Hello, everybody. Welcome back. So since we don't have a lot of time to review for the METOC test, I thought I'd go through the study guide with you. So here we go. Hang tight. First one. Know how moon phases and Earth's rotation affect tides. How and why do tides change daily? Why do the pattern of tides also change on a monthly cycle? So first off, know your moon phases. Going from new moon to waxing crescent, first quarter, waxing gibbous, full, waning gibbous, third quarter, waning crescent, back to new. So the reason for this is the moon's revolution around the Earth. Tides are caused by primarily the moon's gravity, but also the sun. So high tide will always be towards the moon because the Earth rotates 24 hours a day. You have two highs, two lows. Also, based on the alignment of the sun, Earth, and moon, you can have different types of tides, spring tides or neap tides. Spring tides are straight line alignment during new and full moon. Neap tides are your right angle alignments, first quarter and third quarter. So what I did is I pulled up the tides for Virginia Beach from, let's see, April 1st through April 30th. And I also looked at a lunar calendar and aligned what the moon was like during April. And you can see the alignment here. So April 2nd was last quarter. You have your neap tide, your right angle alignment, where your high tides aren't quite as high and your low tides aren't quite as low. The new moon on April 9th is your spring tide, highest highs, lowest lows. April 17th, first quarter, again, neap tide, not so high highs, not so low lows. And then finally, again, spring tide, full moon on the 24th, highest highs, lowest lows. Understand the relationship between latitude, solar heating, and global wind. So during the course of the year, as the Earth is traveling around the sun with a tilt of 23.5 degrees, different parts of the Earth are receiving direct heating. So let's start with June 21st. Around June 21st, that's the summer solstice. If you're at the Tropic of Cancer at 23.5 degrees north latitude and look straight up in the sky, the sun would be directly over your head at noon. June, July, August, September, we have our solstice at the equator. Again, sun directly over your head. The December solstice, around December 21st, if you were at the Tropic of Capricorn, 23.5 degrees south, the sun would be directly over your head at noon. And so the sun just makes this transit back and forth around the equator, making it the hottest part. That also creates an area of intense low pressure at the equator. Then, because the coldest air is at the poles at 90 degrees, it's also your area of lowest incoming sunlight, lowest angle of incoming sunlight. You have consistent high pressure. And so you look at the pattern, low at the equator, high at 30, low at 60, high at 90. How does the Earth's rotation create the Coriolis effect? And then what direction is the Coriolis force in the northern and southern hemisphere? The Earth rotates. If the Earth did not rotate, wind would just move from high pressure at the poles to low pressure at the equator. But it does. It rotates 24 hours a day. This creates a Coriolis effect so that air north of the equator is deflected to the right because of our counterclockwise spin. Below the equator, air is deflected to the left. And it doesn't matter which direction the air is moving in the northern hemisphere. If it's going from the equator to the pole, it curves to the right. If you're coming from the pole to the equator, it also goes to the right from the perspective of the arrow. Know the general cause of global winds. Know the names and directions of regions of global winds, the location of the intertropical convergence zone, and how it changes throughout the year based on season and direct solar radiation, and where low and high pressure regions predominate due to convection or Hadley cells. So let's start with the general cause of global winds, of course, is the sun. As the sun heats the equator, air gets very hot there, creates a region of low pressure, air rises. As it rises, it spreads out on top of the troposphere. At the top of the troposphere, spreading out to both directions, and generally sinks around 30 degrees north and south. At the poles, we have consistent high pressure, so air sinks, travels along the surface, and then collides with the air, a convergence, right around about 60 degrees north and south. So this sets up those Hadley cells, your two at the equator, your mid-latitudes, those two, and then the two polars. Anytime air converges, it has nowhere to go but up. And so at the equator, the trade winds, these kind of northeasterly winds, air is converging from those winds and rising up, creating an area of intense low pressure, lots of storms and rain, but not a lot of north-south wind. This is called the intertropical convergence zone, and it changes throughout the year based on seasons, based on tilt. So in the northern hemisphere, it moves more north during summer months, getting closer to the Tropic of Cancer, and in the winter, it will move down closer to the Tropic of Capricorn. It just goes back and forth, back and forth. Three causes of the patterns of global ocean currents and how those currents affect climate. So the three causes for movement in the ocean, as you know: tides, wind, especially those high pressure areas around 30 degrees north and south, clockwise rotation in the northern hemisphere, counterclockwise in the southern, and then thermohaline circulation, the temperature and saltiness of ocean water. Cold and salty water is more dense, so it sinks. So when you combine all of these currents and all these movements together, it can distribute very warm ocean water from the equator closer to the poles, moves it up. First off, this Pacific Ocean gyre, this clockwise rotation, will pull cold water from the northern North America down, keeping places like San Francisco, coastal cities, San Diego, Los Angeles, keeps their water actually cooler and keeps their climate a little bit cooler. Whereas on the East Coast, that same motion, that same clockwise gyre, but this time in the Atlantic, is bringing warm ocean water up. And that actually goes across the Atlantic, keeping Europe a little warmer and wetter than it should be based on its latitude. Know how air masses are named. So the C, continental, forms over a continent, is dry. M equals maritime, ocean, wet. T is tropical, it's warm. And then P, polar. So you put the two lowercase and the two of the uppercase, and you got it. Maritime, polar, cold and wet and cold. Maritime, tropical, warm, moist. Continental, tropical, hot, dry. And then continental, polar, cold and dry. Those are the main ones that affect us here. You also have continental, Arctic, very cold and dry. But the main ones that affect us, the maritime, polar, of course, in the northern Pacific and Atlantic, continental, polar, up towards Canada, and then maritime, tropical, very wet, warm, tropical air. And that brings us to fronts. Know that a front is a boundary between two different air masses, particularly continental, polar, and maritime, tropical for us here. So characteristics, we'll do warm front first. Warm air is advancing onto cold. The cold is denser, so it acts like a wedge, forcing the warm air up. And then you have this progression of weather and cloud types going from your wispy cirrus clouds to stratus clouds, and then possibly the dreary type rain. Your temperature will typically go from cold to warm as the front advances. Cold fronts are opposite of that. Cold air is pushing its way onto warm. Cold air is a bully. It acts like a bulldozer. It forces that warm air up very, very rapidly, causing cumulus clouds and could eventually form into cumulonimbus and severe weather. So here your rain is not the dreary rain, it's much more the intense. Could even be thunderstorms. So your progression of temperature will be going from warm to cool. Happens a lot in the summer. Now the following about winds. They are the strongest when the gradient is steep or tightly spaced. So here is just a nice representation of isobars marking areas of equal pressure. When you have, and it doesn't matter if it's high or low pressure, but when you have isobars that are very close together, it has a steep gradient. In other words, the air pressure is changing very rapidly in a shorter space. That's going to increase your wind speed. Whereas a gentle gradient, where the isobars are more spaced out, lower wind speeds, just like topographic maps. Know the following about winds. They move from high to low pressure. Absolutely, always. High to low pressure, doesn't matter what hemisphere. Are named based on where they're coming from. Westerlies come from the west. Easterlies come from the east. Sea breeze comes from the ocean. Mountain breeze comes down a mountain. A valley breeze blows from the valley and up. They're always discussed in where they come from. So if you have a northeast wind, it comes from the northeast. Synoptic plot is wind speed and wind direction is indicated by the flag or the arrow. So the direction is the line. Of course, the little notches are the speed. And then how air rises and sinks based on pressure. This is your vertical motion. High pressure, again, doesn't matter what hemisphere, high pressure air sinks, low pressure air rises. When it rises, any water vapor that's in it can cool, expand, and condense into clouds. Know the following about air pressure. Measure with a barometer. See it here on the left. Low pressure, bad weather. High pressure, nice. Low pressure, wet. High pressure, dry. It is indicated in the top right of a synoptic plot. The basic rule is if it's less than 500, then you would add add a 10. If it's more than 500, you add a 9 in front. So for example, 138, it's less than 500, put a 10 in front, decimal at the end, it's 1013.8. And again, isobars, lines of equal pressure. We do this in order to identify how the wind is going to move horizontally. Here, this low pressure cell, wind is going to move counterclockwise. If you know the temperatures around the area and how quickly that changes, you can also identify fronts. The relationship of air pressure with altitude. As altitude increases, air pressure decreases, and it pretty much decreases at an exponential rate. How surface wind in the northern hemisphere move around high and low pressure? Well, high pressure moves clockwise, low pressure moves counterclockwise. That's all. High pressure, also air is moving out, sinking and moving, and then low pressure would be in and up. In the southern hemisphere, that horizontal motion, the clockwise, counterclockwise, flips. So your low pressure actually moves clockwise in the southern hemisphere, high pressure counter. Know the following about clouds. They can indicate fronts approaching. So again, with warm fronts, you typically get cirrus clouds first, and then your stratus with rain. And for cold fronts, you typically get those cumulus to cumulonimbus. Clouds need something to form on because they're actually made of liquid water, not water vapor. Water vapor is invisible. They end up condensing when conditions are right, when dew point is reached, onto condensation nuclei. And this can be a ton of different things. It could be pollen, it could be dust from volcanic eruptions, dust from fires, salt, but it could also be things like aerosols, very small particles, sulfates that could be released into the atmosphere from lots of different places, natural and man-made events. The naming convention for clouds, just know the main three. Cirrus means wispy, high level. Stratus, your flat ones, and they can be mid or low level or high level, but stratus just means flat. And then cumulus means puffy. Humidity. The difference between absolute and relative humidity. Absolute humidity is the actual measure of water vapor in the air. Relative humidity is a percentage. It's how much water vapor is there in the air versus how much could there be. And so in this little diagram, when their water vapor is completely saturated the air, it's 100% humidity, so on and so forth. The dew point is the temperature at which air will condense and go from water vapor to liquid water. So the difference between the temperature and the dew point is indicative of relative humidity because as those two numbers get closer together, that means the air is going to become more and more saturated with water vapor compared to what it can hold. So if your temperature and dew point are the same, it's 100% humidity, it's probably raining. When those two numbers are very far apart, then the air is going to feel very, very dry. On a synoptic plot, temperature is in the top left, and sorry, I gotta make sure I move this out of the way, and the dew point is in the bottom left. All right, know your atmospheric characteristics, 78% nitrogen, 21% oxygen. Carbon dioxide is very, very, very small amount, 0.04%, but it has a huge effect. Most of those other gases, that 1%, most of that is argon. It's that 0.04, that's all your other stuff. How the atmosphere has changed over time. So basically, what you need to understand is that our first atmosphere was primarily just captured gases, and then volcanic releases of gases. So it's very toxic atmosphere. Once the ocean formed, either through water vapor coming from the interior of the Earth or comets or combination of both of them, and our oceans filled up, life took hold pretty quickly. One of the biggest changers of the planet, our first geoengineers, were those cyanobacteria, those photosynthetic blue-green algae, which created so much oxygen and oxygenated the oceans, and then that escaped into the atmosphere, and then, well, we get the picture. We end up where we are today. Layers of the atmosphere, very basic stuff. Troposphere, lowest part where all weather occurs, temperature decreases with altitude. Stratosphere, this is where the ozone layer is. Ozone protects us from UV radiation from the sun, makes life on the surface of the Earth possible. In this part of the atmosphere, temperature increases with altitude. Mesosphere, very thin part of the atmosphere, but there's enough molecules there that when you have an object flying in at 17,000 plus miles per hour, it starts to ablate, burn. And so meteors burn here. Temperature cools with altitude. And finally, the thermosphere. It's very thin. It gets hotter with altitude, but very, very, very thin. And it's the hottest part of our atmosphere. But again, almost no molecules. Excuse me. Oceanography overview. So global winds create the global currents on the sea surface. Just like I said, around 30 degrees north and south latitude, you have pretty consistent high pressure that's going to rotate clockwise. And that's going to help create those gyres, the North Pacific and North Atlantic. In the southern hemisphere, same kind of conditions, but it's going to go counterclockwise. South Atlantic, Indian Ocean, South Pacific. Deep sea ocean currents, those thermohaline currents, are driven by density differences due to temperature and salinity. Colder and saltier is denser. So if you think of it forming in the very far north, ice forms, the water stays cold and salty, and so it sinks, and that kind of starts the current moving. Compare and contrast hurricanes and tornadoes. Well, there's lots of information here. I'm not going to read it all, but basically hurricanes are tropical cyclones. They form in warm ocean water around summer to fall. That's when the ocean water is the warmest. Tornadoes, of course, more spring to summer, but they can actually form anytime. They're much smaller scale. Hurricanes you can measure quantitatively because they're pretty long lasting. Tornadoes, not so much. They're so fast you have to measure their damage qualitatively, very similar to Richter versus Macaulay, as you recall. They both spin. They're both cyclones. They're both very damaging, and they're both categorized by wind speed. It's just how you get that information is different. All right, sea breeze versus land breeze. How and when do they occur, and how are they similar or different to monsoons? So these air-sea interactions are both due to the same underlying principle, high and low pressure. Also, the specific heat of water versus the specific heat of land. So starting with your small scale land and sea breezes, something that affects us here daily. During the day, the land heats up faster than the ocean. That creates an area of low pressure around on the land, whereas over the ocean, it'll be higher pressure, cooler. Air always moves from high to low, blows from the ocean. It's called a sea breeze. At night, the process reverses because the water has held on to that heat energy, whereas the land lets go of it very rapidly, creating high pressure over the land, low pressure over the water. It blows from high to low, from the land to the ocean. It's very similar to monsoons. Monsoons is a condition where in the summer, the land heats up faster than the ocean. And so over land, you have a pretty consistent low pressure, higher pressure from the ocean. It brings that moist maritime tropical air in, creating a lot of rain. In the winter, the process reverses where you have pretty consistent high pressure over the land because it's cooling off faster, where the water is warmer. And so Air always moves high to low. It moves from the continent out to sea, very dry. The land and sea breezes occur daily. Monsoons are a seasonal occurrence. What factors, move this out of my way. Oops, sorry about that. Back. What factors affect climate of a region? And then how do these factors specifically affect climatological temperature and humidity? So the main factors that affect climate, I found this nice little mnemonic device for you, LORN: latitude, ocean current, wind and air masses, relief or topography, and then proximity to water, nearness to water. So all of these together, latitude's your biggest determiner of climate. The higher your latitude, the cooler you are. Ocean currents, if they're bringing warm air, you're going to stay warmer. If they're bringing cooler water, you'll stay cooler. Wind and air masses, where you are depends. Your latitude can also determine where those global wind, how they interact, and the different types of air masses that are interacting. Relief is topography, for example, rain shadow, and then nearness to water. So with the high specific heat of water, you're typically, you're not quite as high temperature in the summer, and you're actually warmer in the winter. Sorry, I skipped one. Elevation. Elevation, as you increase altitude, of course, you get in the troposphere, it gets cooler. And so you could be literally a tropical rainforest at elevation close to sea level. And then as you go 5,000 feet up, you can transition into completely different biomes. Rain shadow. Rain shadow is created due to relief topography, a mountain. So on the west coast, we have a pretty consistent movement of westerly winds, bringing moist air from the ocean and moving east. So when it hits the Rocky Mountains, it's forced up. As that warm, moist air is forced up, it cools, condenses, precipitates, and it rains back down. This is why, the San Fernando Valley in California is so much greener than the other side. The other side is going to be much drier because it doesn't get that amount of precipitation because of the rain shadow. The difference between weather and climate, actually very simple. Weather is your day-to-day change. Climate is at least a 30-year average and more. So you can track your temperature and precipitation and air pressure and all that kind of stuff. That's your weather. That's your day-to-day. Take those same measurements and look at them over 30, 50, 100 years. That's your climate. What is albedo and how does it affect temperature and climate? Albedo is a measure of reflectivity. It's a quantitative measurement from 0 to 1. A low albedo means that it's a darker surface. It's going to absorb more radiation. A high albedo means it's going to reflect more. So when it comes to Earth and climate, ice reflects a lot more than land or ocean, which absorb more. So the more ice, the higher the albedo, the cooler you get. And Drinky bird. How is it analogous to METOC processes? Well, there's a lot going on here, right? The easiest and fastest and best one, and the reason why I introduced it, why we introduced it during air-sea interactions, is very simply the movement from high to low pressure. When you get the bird's head wet, there's evaporative cooling happening. So it's just like the sling psychrometers, the wet bulb. As long as the air is not 100% saturated with water vapor, 100% relative humidity, water will evaporate. The drier the air, the faster it evaporates. But when you get that bird's head wet, water evaporates off of the head, cooling the head, creating lower pressure, cooling the head, and actually the liquid inside condenses and falls down, kind of like rain. As it happens, it creates a tiny amount of low pressure. Things like to move from high to low pressure. So there's higher pressure in the bottom, lower pressure in the head. The liquid moves up, and of course, then it's just tilting. So the biggest thing is high and low pressure, but you can also talk about Drinky bird in other deeper terms like evaporative cooling, dew point. Once the temperature in the head reaches the dew point for that substance, the liquid condenses. There's another one. And then it rains. I don't know, does he have a brain cloud? Maybe, should probably go throw him in a volcano, I guess. But it condenses, drops down, creating lower pressure in the head, higher pressure in the bottom. The air moves up. Or, excuse me, the dichloromethane or whatever it is moves up. And I think that's it. That's all I got. If you have any questions, please let me know. Good luck.